And we're recording now?
Yes.
Okay, good. Okay, guys, while I open the test that we're going to work on today, I was just going to tell you to please review the last two videos we made for you, where you had two loads in parallel, because that's going to be one of your test questions. So make sure you understand how to do that. I think Nick did a great job at explaining that, and Easton and I did too. So if you practice your old test, practice that exercise because it's not going away anytime soon. Okay, make sure you understand it. Use as many decimals as you can. And let me get your test going here. Nick, so I'm going to let you explain the first maybe 15-20 minutes of this problem, if you don't mind, and then I'll take over.
Okay, so in this problem, we're asked to first impedance match, and then what we'll have to do is we'll have to go on and just figure out what the transmission line will look like with that impedance match, and we'll have to find the power delivered to the load and the power with the impedance match. So the first thing we'll do when we're impedance matching is we'll first have to recognize what the load is. So if we look at what is given right now, the load is a capacitor, 1 picofarad capacitor. Oops, that's the wrong color. 1 picofarad capacitor. A 1 over 4 pi, that's a very weird number, right? 4 pi squared micro Henry inductor. So we'll just do E minus 6. Inductor. And we have a 300 ohm resistor. So this is all connected in series. That's very important to recognize. I missed a question because I didn't see series once, and it was parallel. But don't be afraid. Just make sure you read the problem very carefully. And what we can do is we can just draw this new load over here. So we'll draw the capacitor, the inductor, and we'll draw the resistor. Okay? And we'll leave that there for now, okay? The next thing we want to find out is we want to find out what frequency we're running at. So what we'll do is we'll first highlight the things that are important to frequency. We'll look at the guided wavelength is 0.15 meters. That's very important. So what we can do is we can say lambda g is equivalent to 0.5 meters, or excuse me, 1.5 meters. And then after that, we'll have to figure out, okay, so what is the wave propagation, or what is the wave speed on this transmission line? And it's not trivial, right? It's not just C equals, 3E8, because there is some relative permittivity. We have to figure out what that does to the transmission line. So we can solve for the wave propagation speed as 1 over the square root of mu e, or mu epsilon, and that's simply given because we have this right here, because this right here completely defines what's going on between the transmission lines. So what we're looking at here is we're not looking at what copper it is, or excuse me, what metal it is. We're just looking at, okay, what's the dielectric going to do to the transmission line, the E field that propagates. After that, we can write this out as 1 over the square root of mu naught. So that's our free space, I believe, permeability. And then we'll do epsilon r, which is our relative permittivity, and then we'll do epsilon naught, which is our free space permittivity. Okay. And now what we can do here is we can make this simplification. So we don't actually have to calculate what mu naught is or what epsilon 0 is. What we can do is we can recognize that the speed of light is exactly defined as 1 over the square root of mu naught epsilon naught. And so what we can do is we can then write this as c over the square root of epsilon r. And then by doing that, we find out that this is, we can then actually use this simplification, so you don't have to use the big number. You can just use 3.8 meters per second. And then we can do the square root of 4. I'll just write that square root of 4. And then what you get is 3 over 2 E8 meters per second. You guys understand where that came from? It might have seemed a little bit rushed there, but we were just finding the propagation of the wave, the speed. After finding this, we can then refer back to what lambda is defined as. Lambda is equal to the propagation of the wave over the frequency, correct? Yes. So since we know the propagation of the wave, we know the lambda because it tells us that the lambda on this transmission line is 0.15. So what we can do is we can just say F, frequency, is equivalent to UP over lambda. And this is the guided wavelength, so that's okay. Then what we see is, all we have right here is 1.5 E8, that's just 3 over 2, right? E8 meters per second. And then we'll divide this by 0.15 meters. Okay. Then what we see is that the meters will cancel out, so then we're just left with 1 over second, so that's hertz. So we're already on a good track. And then what we can do is we can see that this is 1.5 E minus 2. And then this then becomes, when you multiply this out, you then get 1 E9, or 1 gigahertz. Hope that made sense.
Yeah, so I want to point out here, in this problem, you're big boys now, you have big pants on, and your lambda is no longer just a variable lambda attached to your length. You actually found the value of lambda, so make sure you compute it and use it in your calculations.
Yes, it's very important to compute it. It's one of the most things that could be easily missed on the problem. Like if you didn't see this on this problem, you would have been stuck here figuring out what lambda was. Okay, after figuring out what the frequency is, we can now go ahead and figure out what the load is, right? Because originally we didn't actually know what the frequency was, so we couldn't compute what the impedance was for these two components right here. Now we can do that. So what we can do is we can write out the impedance for these guys. So I'll start with the inductor. So we have ZL is equivalent to the inductance, which is J omega L. And then we have the capacitor, which is plus 1 over J omega C. And then we have our resistance, which is just 300 that was given to us. Okay. Computing our inductance, what we can do is, we don't even need to compute anything. If we plug this into our calculator, it'll be much easier because we'll see that something really strange happens. So we'll just write out 300, so that's our ohms. And then we'll get our reactance right here. So writing out the capacitance first, we see this is J 2 pi. I'll just write E9 for gigahertz. And then we can multiply this by 1 E minus 12 because we're given 1 picofarad. And then what we can do is we can add the inductance. This will be J 2 pi E9. And then we'll see that this is multiplied by 1 over 4 pi squared E minus 6. And then this is that I believe that's it for that one. Okay. Computing this into our calculator, it shows us that something really weird happens. I had to figure out if it was right, but it appears that actually, our load impedance is just 300 ohms, which means that there's no reactance in this load at all, which means that even though there still is a capacitor and an inductor in there, the impedance cancels out. So this makes it very easy for us. We don't have to worry about, like, plus some small number or some really large number. It's very simple. So after finding your load impedance, what we can do now is we can focus on impedance matching. And so what we'll do first with every impedance match is we'll try to find the lambda. Excuse me, the gamma, the reflection coefficient. That is, of course, ZL minus Z naught over ZL plus Z naught. Given in our
I think what you're writing is invisible on the screen.
Oh yeah, sorry. Yep. So that's just gamma. And then if we go back up, you don't worry. It says we're told a 50 ohm lossless transmission line, so that means that Z naught is equivalent to 50. So what we can do is we can just write 300 minus 50 over 300 plus 50. Solving for this gives us a lambda of 0.71426. And what we can do now is we can solve for our theta prime. So the equation for theta prime is known, it's in the book as well. It's just the plus minus of the arc cosine of our magnitude of gamma. Luckily, it's just a real positive number, so we can just forget about the magnitude, just leave the negative there. And we'll get something plus or minus 2.3664 radians. Make sure to include the units as well, just for completeness. After solving for this, what we can do now is we can solve for the length. Since we know our angle of gamma, which is just 0, right? It's not complex at all. It's completely real. What we can do now is we can say d1 and then d2. d1 is, of course, equivalent to lambda over 4 pi. This is the same thing for everything. Do gamma angle and then prime. I'll write the same thing down here. And what I like to do is I like to write the same thing down both times. And then when I'm writing or when I'm choosing my theta prime, because we have two values for theta prime, I like to say, let's see, yeah, for this one I say positive, right? So I choose the positive number over here. And then for this one I say negative, I choose the negative number over there. Solving for this, for when gamma is, when I get the positive value from theta prime, I get minus 0.0282468. And then we have to add plus lambda over 2 because it is negative, right? We can't, negative lengths really don't exist, right? They don't really have a conceptualized idea here, so we have to make it so it's positive because it stays within the transmission line. So now we're adding lambda over 2, and this then of course gives us 0.0467. There are some decimals after here, but right now I'll put them down here, 532. And then meters, of course, because we're dealing with length. And then for this next one, what we'll see is that this is equivalent to 0.0282468 meters, which is handy for us because we can see that this is actually shorter than the other length that we calculated, right? Even though we got this result right here, you could have gotten this result first. You still need to calculate the other length because this could have been shorter. In fact, it wasn't, but we have to do both just to make sure. Okay, after solving for this, the shortest length, what we'll do is we'll set this as our shortest length. Yes?
Okay, and one more thing that I would add in writing this step is that here, Dr. Tuacha, and somebody asked me this question in a chat, so if you're out there, I hope this answers your question. Dr. Tuacha might say, the transmission line is not accessible of, I don't know, at certain point. Let's say this is your transmission line and here's your load. And he says, from here to here, there is a box blocking access to the transmission line, so we cannot connect anything on this area. Oh, sorry, let me control Z. So if you're length you calculated, this one or this one, is in between that area, then you might need to keep adding lambda over 2 until you're outside of that length. And I hope this answers everyone's question, or what do you do if you have no access to the transmission line at some point. So you keep adding lambda over 2 until you come out of that place and you're somewhere in these points.
Yes, that's so important. Mark, did you have a question?
Yeah, I was wondering where the theta r came from. I don't know if I noticed on the calculations where that
Oh
was.
yes, so theta r, I think it's probably theta r or something like that in the book. Theta r, theta gamma, because we're dealing with a gamma that is equivalent to 0.714, it's completely real, right? So there's no complex component, which means that the phase of this is just 0 degrees, right? If you were to draw it on the axis, you have Im, and then you have real. It's completely real. So the angle is 0 degrees or 0 radians.
Thank
Does
you.
that answer? Okay, good. Answers your question. Okay. Next, we'll compute the susceptance, the unit susceptance of the so now we figured out where we want to solve this at. We know what the length, the distance is. Now we need to compute the unit susceptance by finding after we found the gamma. So we just have everything right now that we can solve for. Unit susceptance, I'm talking about BS, which is the 2 gamma sine and then the theta prime. And this theta prime is the one that you used right here. So since this was the shortest length that gave us, I'm going to put it right there. And then we're going to divide this by the 1 plus gamma squared plus 2 gamma cosine of, and then of course our theta prime that we used as well. So this guy is going to go right there. Solving for this, we obtain the value of the unit susceptance of minus 2.04124. Okay, then solving for the next part, this is how I solve it, so you guys may solve it differently. The idea of conductance is related to this, but I don't think about that when I'm solving for this. I just go straight towards solving for impedance again. So the z stub, what we'll do is we'll then say z naught over j, the susceptance. And then what we can do here is we just get this value as 24.4949i. And don't worry, we'll share this particular problem with you guys so you guys can work it out yourself as well and make sure you guys get the exact values. Okay, so if we can go back up to the original problem, we can see that it was asked of us to find a shorted stub. So how she highlighted it, made sure shorted stub. So that tells us, okay, so we're going to have to use this particular equation for that one. And the equation we'll use for that one is the stub length, which we'll just call LS for shorted stub, is equivalent to the lambda over 2 pi times the arctangent of our stub impedance, desired stub impedance, and our j omega, which is just what was originally in there. Solving for this then gives us a length equivalent to 0.0108, some numbers. It's very small, but because of this very small length, e minus 3 meters. That is your shorted stub length right there. So that should complete part A. Do you guys have any questions?
What I was wondering, what's the for short stub length? Are there other variations, or what does that mean? A difference versus just calculating the length of the stub period?
Oh, so there's since we have the z in equation right at a particular location, say z in at L, is equivalent to the z naught whatever zl plus z naught j tan beta L, right? What this equation is right here, this is a derived form where the impedance is, the ZL is 0 because this is the stub, the shorted stub, so no basically no impedance. And what we're solving for now is we're solving for the L in the tangent beta L, and that's why we have this tangent right here. You can use L'Hopital's rule to help you derive this formula as well. I think Dr. Twacha has gone over it. He may have gone over it before impedance matching or while impedance matching. For us, he went over it before impedance matching. Does that answer your question?
I mean, I'm kind of halfway there, but I think I can piece it together.
Okay. And I highly recommend that you actually just have a program on MATLAB just do this all for you, because I mean, while I just sat here and just gave you the answers, it would have taken me time to write all of this out, type it into my calculator, and then make sure I got the right result. But with MATLAB, I could have easily just I could have easily just done the stuff at the very top, solving for the frequency, solving for the load, and then I could have my program solve for gamma, and it just does everything super quickly. It's super recommended. It saves you so much time.
Yeah, and I would say, so if you remember your lab 3, Mark, and I don't know if this relates to your question, but he could ask for two things, either short stub or open stub, which you did both in your lab, I assume, because they asked you to test both. And if you were asked to do the open stub, then the only thing that would change is, let me find out what equation that was. For open, your length is equal to, and I'll put it here. So length of open stub is, I don't know if this has anything to do with what you were asking when you said is short stub the only thing that could be. No, I mean, he could have said open stub, which not usually used, but this is the equation. So as you can see here, the difference is that the Z naught is on the top and this guy is in the bottom. And this all goes back to what Nick was saying, that Dr. Twacha derived this in class for both the open and short condition. And like Nick said, in impedance matching, all the equations are the same. They really don't change. So you should have either on your calculator or in MATLAB a program for at least, I mean, this equation is always good to have stored somewhere. Your data prime, I mean, and if you don't want to have it anywhere because you're not super coder person, then just make sure you have these equations in this order because they won't change. Just make sure you're using the right values all the time.
And that bottom part of the Z naught, is that a ZSJ or what is that?
Yes, that's a J. So make sure you don't forget the J because I forgot it once and it wasn't good.
Okay, thank you.
Thank you. I'm embarrassed. I should be writing nicer. Nick's using his mouse. I'm using my pen. I'm embarrassed now.
Oh, I'm sorry.
Okay.
So were you going to work the transmission line portion?
Yeah, I'll go ahead and take that over. So so any more questions before we move on the transmission line and for the impedance matching, and for any of you who had difficulty with your lab, you can go over this process again and you'll find out maybe you're the right answer. If you didn't get it right for the lab, this could help you for sure. But let me ask, did you guys, how was that lab? Did you end up figuring out then?
I did not. I had to ask after it was done to get help with the TA to figure out a way to solve it.
And did he help?
He provided me a video I watched which solved it a different way than this, but I did figure out a way to do it.
Okay, good. Okay, so let me see where I want to write these. I guess over here. So now that we have impedance matching done, now basically part B is just a transmission line problem, just like any problem you've done in test 1 all along. So as you can see here, the question is determine the time average power delivered to the load resistor with impedance matching and the time average power delivered to the load resistor without impedance matching. So you have to solve 2 transmission line problems basically. And if you are comfortable with test 1, then this will be easy cake for you. If you're not, don't worry, we're gonna figure it out here. So I'm gonna start with the transmission line with no impedance load. I always do it in that order, even though it's not what he asked for, but for me it's easier because it's like just the regular transmission line before anything happened. Okay, let me zoom in a little bit. And let me see if we have a value for CG. Yeah, we have a CG, so don't forget about CG. And I'm gonna stick to the convention we've learned this time. Oh, thank you, Nick. I hope you're all familiar with these. How did you guys feel you did in test 1, by the way?
I did well. I checked my answers, at least on the first one. The second one I didn't finish, so that's something.
And that's completely normal. I never finish any test, I don't think. I was never able to finish. So let's write down what we know. So we're given BG. And then, so like Nick said, Z load without impedance matching after you compute all your inductors, capacitors, and resistor, that is still just 300 ohms. Let me see what else. And our transmission line is 5 meters. So actually I should put here -5. But we have a lambda value, so this is 5 times lambda, which I think on my test, what I did was compute the actual value of that length with lambda included, so I didn't have to worry too much about it. Let me see if I did that, or I did not.
Would it be, to solve for the length, you would divide 5 by lambda? And then reference lambda?
What do you get for that? I don't think I wrote it down anywhere.
In terms of lambda, I got minus 33.3333 lambda.
Sounds like something you would get.
It was actually 33.333.
Okay, 33. Okay, so can you tell us one more time what would they need to do? Do they need to divide 5 by lambda?
Yes, because if you divide
Okay.
5 by lambda, then you get something that can be represented as like a length, but then you want the length to be equal to 5, so you have to multiply by lambda to get it back.
Okay, and that's going to be helpful for you guys in your binom plus equations and all those equations that we've derived earlier in life, where you just plug in where the lambdas cancel. So that could help you. If you didn't remember that, then you could multiply these by lambda and then just remember to add lambda into your 2 beta equation, because remember beta equals 2 pi over lambda. And if you forget that value, then it's going to mess up your calculations. So either way, so now, so we know BG, and we want to find the average power. So let me just go ahead and write that formula so we know what we're looking for in this problem. Oh God, why am I writing so bad? So if you see here from the power equation, oh God, we're basically, we need to find VL voltage at the load and current at the load. And you know, that's basically just a transmission line problem. So if anybody here remembers, what is the most important thing that will help us find the voltage at any point of the transmission line? I'm gonna look for participants here. Let me see who's there. Gonna call out someone randomly. T, you remember? If T's here, I don't know. Well, what about Tabita? You know what we need to look for so we can find the voltage at any point of the transmission line? Mark, anyone?
Just looking for like a particular value, not an equation or anything.
Yeah, just not looking for a value even, just the term that helps us find voltage.
Equations. Aren't we supposed to look for V naught or something?
Yeah, excellent answer, Mark. We are, remember, in any transmission line, our goal is to find this guy, usually V naught plus, because once we know that, we know the voltage at any point of the transmission line, okay? Because we just know that the relationship between this guy is just, it can help us find the voltage at any point of the transmission line. Does that make sense? Mike, I'm glad you remember that. That's good. Okay, so since that's what we're trying to find, anybody remembers other equation that could help us given that we know what BG is? And if you did test 1, I mean, you should know this. This is not news to you. So can somebody tell me, given BG?
We can solve for Zn, I think, because we
Yes.
have Zn is easy.
Yeah, excellent, Mark. So if we know BG and we know B, and why can we solve for Bn? Because it's a voltage divider, right? That's super easy. And so BG is basically this relationship, which is nothing but a voltage divider over Zn, right? So if I want to solve for Bn, which I know, the reason why I want to solve for Bn is because I know Bn is the voltage at the most left side of my transmission line. So if I know that, then I will be able to solve for B naught plus eventually, and then B load. So that's the reason why I want to find V in. Okay, that's our big picture. So if I want to solve for V in, all we need to do is solve for V in that equation, which is VG Z in. And there's people that do these in 2 steps, so they just actually plug these in the B naught plus equation. That's very efficient. I like to do it step by step. So, and from here, and I guess I should have started with this, but I kind of wanted to give you an idea of why we're doing what we're doing. But the first things we always solve for in the transmission line are gamma and input impedance, right? Because we're gonna use those in basically every equation that we're working on. So make sure you find your gamma. There's no tricks to these. You should know these. These equations should be on your MATLAB code that you're experts at right now. So your gamma has a value, and actually you saw for this gamma back in the first part of the problem with Nick. So your gamma was 0.7. This value may not be important because it's basically 0, but you can decide if you want to stick with it or not. It won't really change your answers that much, but because I just plugging everything in my calculator, I just went with it.
Why do we have an imaginary value? Because the gamma we got when he did it was without the imaginary.
It should be completely real. Yeah.
Okay.
So, sorry, I didn't mean to interrupt you. One second.
I mean, it's basically real because it's so small, you can't ignore it, but well, I won't put it so we won't get confused. And then our Z in value, I'm not gonna compute that for you. You guys are big boys, you know the formula and everything, so my Z in was big boys and girls. Sorry, everyone. Okay. Okay, perfect. So from here, V in, like I said, is just plug and chug this guy here. So your B in is nothing but and from here, so if you remember the V naught plus equation, which actually comes derived from, so V in is equal to V of negative L, which equals B naught plus e to the negative j beta L so if I solve for B naught plus here, I end up with and I like to remind you, I know that if I'm solving for these equations the way I derive them and Dr. Tuacha derives them, the value that we're going to put here is actually has a negative in front, okay? Like right here inside these parentheses. The way we derive it is for you to plug in a negative value here, okay? So do not get tricked by this other negative here that already exists. You still have to put in this one here if you're using Dr. Tuacha's derivation. And so based on our calculations, this guy's going to end up being okay, and we can solve for BL from here since BL is nothing but okay, so this is a trick question. So what is BL? I mean, and by that I just mean what is the simplified equation for BL? Anyone?
If you plug in L, what do you guys think will happen to the exponentials?
I don't know, it might have to do with all the crazy highlighting and stuff, but I'm assuming it's, the V at, or I already forgot the question, I'm sorry.
Okay, go ahead and plug a 0 for LT right here. What will happen?
I think it'll be equal to V naught plus.
Okay, e to the anything to the 0 power. What's e to the 0 power?
1.
1.
Okay, what else?
Gamma 2. So it'd be, yeah.
Good. Okay, and this is an equation you guys can just memorize, write down, have stored somewhere. For me, it's just so intuitive to understand the relationship between voltage at any point of the transmission line, but you can just know these equations, the VL, the voltage at the load, because of the location is 0, then these terms are 1, and that's why you end up with this simplified version. Is that okay? I like everybody participated. Good job there. So plugging what we know, because you guys found all these values already. So your BL ends up being 42.855 minus J74. And then I can easily solve for my power from here, because that's nothing but, I don't even need to solve for the current. All I'm gonna do is VL times the conjugate of BL divided by ZL. And that should give you 12.2449. And this is with no impedance matching. Now, if we put an impedance matching network, what should happen to the power?
Should it not go up?
Yeah, right, because the purpose of impedance matching is to increase the amount of power delivered from the generator to the load, which ideally be the maximum power available, right? So if we didn't have an impedance matching, we have these, we would expect it to go up, right? So if you guys do the next part and you get a different number, you could be like, well, I probably did something wrong. Or you got a slightly bigger number and you're like, oh, okay, that seems reasonable. I probably was in the right path. Okay? So this is the load without impedance matching. So let's go ahead and determine with impedance matching. So the first thing we need to do is actually do our first, so we still have a ZG, and we have a new load here, where this load is ZL in parallel with your impedance, your stub, your impedance of your stub, okay? Obviously, what do you think the length is gonna be of this? I'm not looking for a numerical value, but just intuitively, where, like, how much should the length decrease?
Just by the other lambda value or whatever we found before, maybe?
Yeah, exactly, the distance that you solve for them. Okay, so we will subtract that distance that we calculated before, right? I hope that makes sense. So this is now your new. So in my case, so it was 5 minus, and then you can write this in terms of lambda. I'm not gonna do it. You guys are in charge of doing that, okay? This is just in terms of meters. So what I did was 5 minus your distance of the stop. That gives you 4.97175. And this is in meters. So if you want to later turn this in terms of lambda to make all your calculations smoother, go for it. I'm not gonna do it for you guys because that's super easy. And let me see what. Oh, Nick, can you explain this part?
Yes. So what Montse written here is technically incorrect because when we look at this portion of the impedance, or excuse me, of the transmission line, so this is generators over here somewhere, but we're looking at the matched stub and the load right here. Because there is some length in between here, and that means there's some Z naught. We'd know this is a transmission line. It'd be incorrect to say ZS and ZL. It'd be incorrect to say that the impedance here is ZS in parallel with ZL. You would have to first find the input impedance right here, which is at minus D2.
Yes, Nick is absolutely correct. And actually, I will go a further step and ask, when you do impedance matching, what is the purpose of impedance matching? What happens? What's going to be your new Z load value, or why do you do impedance matching? If your characteristic impedance, your Z knob is 50 ohms, and you do impedance matching, what do you expect your ZL to be? If you did Lab 3, you should know the answer to this.
Be as close as possible to ZS.
Yeah, I mean, they should be the same theoretically, right? The purpose of impedance matching is for the characteristic impedance to match the impedance of the load so nothing gets returned. So I'll just go ahead and go one further step and say that your ZL prime, because we're looking at the new transmission line here, should be 50 ohms, because that was your Z, your characteristic. Because this is right here, your characteristic impedance, right here on the 50. So the whole point of doing impedance matching was to match our load impedance with that. You could calculate it too. You will get a very similar number, something like 49.9999 plus J, something to like the e to the negative 20, which is basically 0. So it's up to you guys. I want to make my life easier, so I'm just going to go with the theoretical value, which is 50. Right? I mean, obviously in real life, as you can see in your lab, that was not that true. But any questions on that? I hope not. So going back to so we're trying to find the voltage at the load again. And this part actually kind of goes back to your test 1 when you have a transmission line with a load in parallel. And if you want to find a voltage here, I don't know if you remember the last review, but there's so many steps involved here. So first we need to find the voltage at this point, and then cut this transmission line into only this section, and then solve it from there. So whatever voltage we find here, we make a new generator, and then we compute the voltage at the load. And that's what we're gonna do here. So we're basically doing 2 transmission lines out of this problem. Okay, does that make sense? Is anybody confused?
If that makes sense.
Okay, since we have impedance matching, there's a lot of simplifications that are going to happen here. So based on our, and again, we know BG, and we want to find the voltage at this location, right? Which is the voltage at the load. And the process is kind of exactly the same as we did just in this portion, okay? But with different values. So V in, if anybody remembers our derivation, which is just a voltage divider. So V in is equal to VG, Z in over Z in plus ZG. And what is Z in here? Because we are impedance matching, Z in equals Z knob. which equals CL. Okay? So I'm going to go ahead, I mean, you can put a 50 there, which is its value. You can leave it as variables. And you can just call them all Z-ins. I'm just doing these to show you the derivation. This is wrong. Don't do this in real life, but I just want to show you what happens. So we could technically factor out Z in here because they're the same value. That leaves it 1 plus 1. So then this cancels, and this is just VG divided by 2. I hope there's no trick in there. So in an impedance matching network, V in is equal to VG over 2. Okay, you can just derive this formula if that makes you feel more comfortable. You can just plug stuff in your calculator and find the value. I just like to see the algebra behind it and maybe simplify my equations before I dive into them. So I'm going to stick with this guy. And from here, VG is nothing. I mean, easy at VG was 50 divided by 2. I mean, 100 divided by 2, that's simply 50. And if you want to find B naught plus, we talk about this. So B naught plus is equal, and let me ask, what is the gamma value for an impedance match transmission line? The theoretical gamma value. And Pratik should be try to hammer these in your head all along.
Is it 1?
Sorry, what was that, Tavita?
Is it 1?
Is it
Is
0?
it? Yes, it's 0. So let's think about what is the equation for gamma? Right? So if ZL equals Z naught, which is what we did in impedance matching, what's going to happen to the numerator?
It's going to be doubled.
Let's
Equal to
see.
0.
It's going to be 0.
Yeah, exactly. So equal to 0. So my gamma value for my impedance matching network is 0. My C in equals CL, which equals C naught, which is 50. And these are simplifications that are going to make your life easier during this problem. Okay, I mean, you could find values for these, and you will get some numbers which are going to be super small. Like if you actually calculate these, you may get a value, but it's going to be like e to the negative 15, which is basically 0. And that's just more stuff you have to plug in your calculator, so more room for error. But if you know the concept of impedance matching, then there's no reason why you cannot just stick to these, okay? So let's see. So now we're just solving for B naught plus. And let's remember the equation for B naught plus. B naught plus is V in divided by e to the negative j beta L, and I should put this guy in parentheses. E to the and what happens to this equation to B naught plus? We can simplify it a little bit, and it's going to end up being I mean, this guy is 0, right? So bye-bye. This guy is 0 because gamma is 0. So this is nothing but B in e to the negative j theta L. Right? So if you find the value for B naught plus, and remember, why why are we trying to solve for B0 plus in this transmission line, in the impedance matching network? Anybody remember? Big picture.
Can you ask that again? Sorry, I can be get lost here.
Yeah, and that's why I just asked this, because in these problems it's so easy to get lost because there's so much happening, you know? So you need to understand, like I remember freaking out probably in this part of the problem because I'm like, what am I even doing? Like, retrace your steps. The goal, remember, we cut our impedance, our transmission line into the left side with our impedance match network because what we're trying to find is the voltage at this location, which then will help us find the voltage at the actual real load, which is what we're trying to find, the power going here, okay? But to do that, we first have to find this voltage, and then we're gonna solve another transmission line once we know what's happening here, okay? So this is just part one of this transmission line that will then solve the other part. And I just want you to appreciate everything that we've did just in this problem. I mean, it's gonna be a long problem, your impedance matching problem, and finding the distance should be the short part, the easy part. What Nick did here, if you have these equations, that's your short part. The long part is this, because if you think about it, we already solved one transmission line here, and from here we're solving one, and we still have one more to go. So it's kind of 3 transmission line problems in one. All right, so everybody okay with the big picture?
I'm okay with it now.
Okay, so going back again, so we're finding B0 plus, which is the voltage at the load, right? Because it's an impedance match network. Because remember, the equation for VL, which is what we're trying to find, is equal to V0 plus 1 plus gamma, right? Everybody remember? We did this just a second ago here when we plug in the 0 for the ease. Yeah?
Yes.
Yeah.
Okay, thank you. So how does this simplify? What is V load of an impedance matching network? There's a clue right here on the screen. How does this equation simplify?
It just goes to VL equals V naught because the R is 0.
Thank you. Yeah, gamma is 0, so it's simply VL equals V naught. So if I found V naught, I know BL. I should be more consistent with my writing, and so BL is equal to V at L equals 0, which is equal to V naught plus. So if I find B naught plus, I'm done with this problem and I can move on with my life. So BL, and you can call this guy VL prime, VL match, whatever you want to call it, so you kind of keep track of everything. This guy is 30.64 minus J 39.5. One thing I should mention again, so be careful what you plug. Make sure you really work this problem today after this review, because I want you to email me if you have any problems getting the answers, because you need to be careful what you plug here. If you put everything in terms of lambda, then you can just do 2 pi times your length times the lambda, and the lambdas will cancel. If you didn't put everything in terms of lambda, then you have 2 pi over lambda, which does exist in this problem, times the length of your transmission line. So please work this problem at home and email me right away if you have any problems getting the right answers. So, okay, so remember, let's back up one more time. The reason why we found this BL is because I want to find the power delivered to the load. So now I found this generator voltage here. So now I'm going to cut my transmission line one more time into only this section. And this should remind you of your problem on test 1, where you have 2 loads. So we're going to cut the transmission line, and this VL here happens to be the generator voltage of this new transmission line. Is everybody see that? The voltage at the load here happens to be the voltage of the generator voltage of this smaller transmission line. Is that okay with everyone?
That's okay with me.
Okay, perfect. So I'll move on. So I'm gonna go ahead and draw that new transmission line over here. And you can call these new transmission line. And this is a baby transmission line. There's no ZG, right? Because we're only taking the right side of the transmission line. So this distance is a baby distance. The length of all of these should equal your distance that you find for your stub, right? Because this is the distance from the load to the stub that you put earlier in the problem. So this is VG, which equals VL prime matched. And can anybody tell me what this ZL value is? Let's see, let's go back over here. Well, I will tell you. That is your original ZL value, which you found from the problem, computing all your impedances and everything, and it just ended up being 300, okay? That is your ZL there. Your Z in here is known from part A. What else? What do we need to know for this problem? So gamma here, because we're solving a transmission line problem, right? Gamma is the same that you found, since gamma is nothing but this guy, it is the same that you found on the first part of the problem back with Nick, okay? You guys remember that, I hope. We found it a long time ago over here. It's this number over here, okay? Oops.
So this new transmission line, because let me just get this right, where we have finished the parallel, well, not technically parallel, but paralleled the equivalent. This is the new impedance match one, bringing it back from the beginning of before the second, this part B, with the load.
Let me try to draw something to see if maybe that makes sense. So we have a transmission line, CG. Then we do impedance matching. We found out we need a stub over here. So the first part of the, actually before I put my impedance match there, the first part, or one of the parts, ask for the power delivered to the load with no impedance match, which is just this that you're looking at. Then the second part asks for the power delivered to the load once you have an impedance match network. So what we need to do is break this problem into 2 transmission lines. One is the impedance match network, which I'm going to draw over here. Which is basically this part. And then the other transmission line, which is this one, is over here. So the reason why we use the impedance match one is to find the voltage that goes, all the voltage that goes from here to here, because there's no voltage going back, right? All the voltage, or I shouldn't say voltage, I should say the power. All the power going here is delivered to this point, but from this point to the load, it's not matched, right? So there will be some reflection, so the power will be different. So then, once we found this voltage here, we use transmission line to solve for this. Now we have this voltage from here, the same. And now we can find this voltage at the load here, and then find the power delivered to the load. Okay, does that answer your question? I don't know if my drawings are making justice to what I need.
Yeah, at least it puts me back on track what we're doing. So realize there's another step in there. So yeah, that's a lot.
Yeah, so what we did here, the first part, what we just solved was the voltage at the load with the impedance match network, which is, I like to either go left side and right side, or big transmission line and small transmission line. It doesn't matter. You can call this one left and right. I like to call big T and small t, because usually the right side is smaller. So we just found out the voltage at the load of the big T. So now we need to go to the small t and solve for that transmission line problem. Okay. And like I said here, you just use your basic transmission line equations. We found gamma. We know what the load impedance is. We have BG. And as you can see in these problems, it's basically the same procedure over and over again, because we've had BG in all the problems. So because we have BG, we can solve for BN, which is a voltage divider, right? And in this network, you don't have a ZG value, right? Usually Dr. Twacha puts something there to help you with your voltage divider, but because we don't have one, then it's obvious that BG is equal to Vn. And if you don't believe me, this is because Zn plus Cg times Bg. If this guy is 0, then these guys are 1, which is just Bg. And so from here, and we know Vg, we solve from the previous problem. Well, the previous, just the step we did a second ago, which is BL matched, right? And so now we can use that to solve for B naught plus in this equation, which is Vg or BL match, whatever you want to call it. And you're going to solve for B naught plus, and this is not an impedance match network anymore, right? So there's no assumptions, there's no shortcuts, you have a gamma value. And so now you can find BL with the real equation, which is B naught plus 1 plus gamma. So here, what I got for VL, and so basically from here, I can easily solve for my power, because my power is nothing but 1/2 real of VL times, actually that's a convolution, sorry, IL conjugate. And so I can also write IL as VL over CL, and for these you should get, for these 25 leak. Yeah, 25 around. I think you can either you'll get some decimals, but it should be 25 watts. Okay, and this is with impedance matching. And remember, so what if we compare this to the power without impedance matching? Should this be bigger or smaller?
Didn't we say that the power for impedance matching was going to be larger than the other one?
Exactly. Thank you, T. So let's go ahead and see if we did right or wrong in this problem. So we have 25 watts here, and we had 12 watts over here. So we more than double. Wait, did we? I think we doubled it. Sorry, math's not my strength, as you can see. But anyways, it increased, right? So even if we probably screw on the calculations, at least we know we're in the right place. Any questions here? That was it. It wasn't as horrible as it looked. So my, like Nick said, my advice is for you guys to have a impedance matching code. I did one back in the day, and I actually did use it for my test, and it just, all it did was gave me the distance, I think. So it was really helpful, because this part, you get it out of the way fast, and then you can focus on your transmission lines, because as you can tell, we work on basically 3. And if you have a code for transmission line, maybe you want to do one where you're given BG, since you can tell that we use BG in most of these. I cannot guarantee that will be the case forever, but it certainly wouldn't harm you. Like if you're given BG, how you find B naught plus, blah, blah, blah. So one more time, guys, I'm going to just kind of summarize what we did. We found the distance of our stub over here. That was not terrible, because we know the equations. We then found the power delivered to the load without impedance matching, which is just a simple transmission line problem with the givens. You're given length, you're given ZL, you find your gamma, your C, your input impedance, whatever. And then for the power delivered to the load with impedance match, we have to break this problem into 2 transmission lines and first find the voltage at the stub, and then use that voltage to find the power delivered to the load. All right. So any questions on this problem?
No questions. Looks good. I'll have to go over it in my own time and make sure, but looks good.
All right, and like I said before, you may want to review. You may want to review the other videos where we did the double load transmission line, because that's definitely going to be on your test. He's going to let you try that one again. And for the Calc 3 question, or I mean Chapter 3 and Chapter 6, I'll say he'll do probably, make sure you know how to do curl, your homework, practice your homework problems. I think he wants to test you more on transmission line other than that, and that will just be more like a bonus. But if you know how to do those curl things, I think you should be okay. Make sure you know how to do cross product, I think. I don't know. Anyways, Well, if there's no more questions, I'm going to go. I know Nick has to go too, and Tuan will have another review coming up here soon. I don't know if Tuan's in this meeting. Oh, okay. Do you want to take over on this meeting, Tuan?
Yeah, sure.
All right. Well, I'm gonna go, guys. I'll leave you to it. Have fun. Please email me if you have any questions.
See you guys.
All right. Can anyone hear me?
I can.
Hello, can anyone hear me?
Yeah, I can hear you. Can
Okay, so how do you guys feel about all of those questions?
it's quite.
I'm sorry.
It's a lot of stuff. All the steps. Isn't there another question to go over, or is that the only question?
No, I'm not gonna do it with you guys. Just there's already too many questions being reviewed, too many example problems. So I think you guys have enough of that. I personally, I think it's more helpful if you guys understand what's going on in this formula rather than just memorize how to do these problem and equation, because it's already there. There's no need to memorize them. So I think what I'm gonna do is that I'm just gonna go over all of the transmission line equation, just the idea of why it is there and what are we gonna do with it. Hopefully at the end of this section, so you would have a better understanding of those equations, so you can use them more effectively, because there's a lot of them, and I understand that it's really confusing and you might feel lost when it comes to those. Okay, give me 1 second. I'll share my screen with you guys. Can you all see my screen?
I can see it.
Yes.
Okay, I think it might we only have let me see how many people we have in here. So 4 of you guys. So I hope that you guys can actively participate in this. It would help. I hope it would help you guys on this exam on Thursday. Okay. So with all the equation you guys have, so let's go back to the very beginning of the transmission line idea. So with what you got learned in circuit classes, this is an easy problem, isn't it? If we want to find out the VL, is essentially just going to be equal to VG, pretty much, and the impedance at this point right here going to be equal to impedance at this point right here, and the voltage also, vice versa. The current going to be the same throughout the circuit. So the problem is that the Kirchhoff law and the other theory that you learn in circuit 1, it is a simplified version of the Maxwell equation. It is simplified because the frequency of the signal is small. So essentially, the physical wire, I think in the beginning of the book, if the physical wire is less than the wavelength divided by 10, much less than that, then you can apply the simplified version of Maxwell equation, which is what you learn in circuit, to solve the problem. But when the physical line is getting larger, in this case, you have the actual power line maybe going from to the power supply plant, maybe going through 100 mile, 500 mile. In that case, then the length would be really long, and it would be maybe greater than the wavelength of your signal, which is in this case going to be equal to speed of light divided for 60 hertz. In this case, then this simplified version of the Maxwell equation cannot be applied anymore because there would be a lot of varying. The voltage at this point right here would be different from the voltage at this point right here. Sorry. So we need to use a different side of equation to account for these changes. Are we clear on that part? Do you got
you rephrase? I think I'm on it. Can you just rephrase it real quick?
I'm sorry?
I think I kind of got it. Can you rephrase it? Just two different power for different lengths of lines. I'm just gonna.
Yes. So okay. So let's just say this is back to your circuit 1 class and physics 2 class. This is just a simple circuit question. We have a source, we have the load, and then we have the current going through that, right? If I ask you what is the, let's say we have point A right here, AB, and then we have CD right here. If I ask you what is the current going through, I'm sorry, what is the voltage at point CD? What do you guys want to have? What is the voltage at CD? VCD, what is it equal to? It's going to be equal to VG over GL, right? If I ask you guys what is the voltage VAB, it's going to be also equal to VG over GL. So the assumption that we have in here is that the voltage across the line, if there is no resistance, it's going to be here. It's going to be the same. The current going through it going to be the same also. We clear on that part, right? And it turned out that these equations, all the Kirchhoff law that you are doing, they are the simplified version of the Maxwell equation. And you can simplify the Maxwell equation when the physical line, the length of the physical wire is much less than, I think, 10% of the wavelength of your signal. It might, I think I might remember the number wrong, but essentially is around it had that requirement. If it's less than that, then you can approximately, or you can safely assume that the current going to be the same, the voltage at those points going to be the same between the, yeah. But in the case of the physical length is greater than the 10% of the wavelength, you could have the case of the power line. The power line had a frequency of 60 hertz. So if you take 10 divided by, I'm sorry, 10 to 10 divided by 60 hertz, you have a number, right? I don't have a calculator with me, but you can calculate that. And if the line is greater than 10% of this value, then you cannot approximate, you cannot safely assume that the current is going to be the same across the line and the voltage would not be changing. In that, or in the case of the physical length, it's just maybe 10 centimeter. It's pretty short, but the frequency that you're working with is really high. Let's say 10 gigahertz, 6 gigahertz, or maybe in the megahertz range. Then again, we cannot just simply use the Kirchhoff law or the simplified version of the Maxwell equation to do it. In that case, you have to develop a new set of equation, which you will learn it, which is the transmission line, to accurately model this power line. Are we clear on that part? Do you guys have any question?
I'm following. I'm clear on it so far.
Okay. If you have any question, just speak up because I'm just here to help you guys. You don't have to stay if you don't want to. And yeah. Okay, let's move on to a different part. My apologize because I'm not really used to using this whiteboard. Anyway. Okay, so back to what we were talking earlier. We said that because the line is the physical line, it is not like smaller than 10% of the wavelength anymore. It could be greater than that. It could be equal than that. So we cannot apply the Kirchhoff law in this case, right? So how are we going to model this? The idea back in chapter 2 is pretty simple. So if the line is too long, you cannot do it. Then what if you just analyze a really small section of the line? Let's say that right here, the total length is, say, maybe 100 miles or something like that, right? Then clearly this is going to be greater than, or maybe it's not going to be smaller than the wavelength, 10% of the wavelength, right? So we cannot use the Kirchhoff law. But what if we analyze a really small section of the line? In this case, going to be like this. This section could just be L prime, just going to be equal to, let's say, 0.1 millimeter, or even 1 micrometer or something like that. In that case, then we can apply the Kirchhoff law into it. So are you guys clear on this one?
Yeah, I'm fine.
Okay, so in that case, right, I'm just gonna share my screen with you so you don't have to give me 1 second, because I found, give me 1 second, let me because I don't want to rewrite the equation, so I'm just gonna paste. Okay. Okay, in that case, right, if I think you already went through in the lecture, if you apply the Kirchhoff law and then all of those stuff, and then you add all of those small sections throughout the line, you would have the equation, which is the telegrapher equation, right? Which is in time domain, of course. So you have lossy equation for the voltage, current, and then the lossless version of that, etc., etc. So in this equation right here, you see there would be two variables, which is z and t, right? Z account for the location. In this case, going to be the location of the value on the line. You have a different voltage, and what time, and what is the time variable of that? So maybe you are, let's say, 10 meters away from the source. You stay in there 10 seconds after the power being sent out, maybe 20 seconds after that, then it would change accordingly. So this is a really complicated equation. It's hard to solve. So our objective is to simplify it even more. So with two equations we have here, what if we assume that this is a sinusoidal signal, sine, cosine? In that case, we can simplify GB down to just one variable, which is right here, right? We just simplify it down in that way, so we don't have to deal with it. So the idea is just that you had the problem is that circuit. You cannot apply a simple equation to it. If you want, you cannot use a simple equation to model the circuit that you have accurately. So you have to deal with a really complex equation. So to make your life easier, you just want to simplify it. So the first step you do is you analyze a small section of the line using a simple equation. Then you add all of them, add all the small section, and you got the telegraph equation, which is a complex equation. So you want to simplify it. So first step is you assume that the assumption you make here is that the source is going to be a sinusoidal signal. So you simplified that. If the signal source is a triangle wave or a rectangular wave, then you will have a different set of equation. You cannot use anything down here anymore. So anything down here under the assumption that will be a sinusoidal, sine or cosine. That's the first assumption that you made, right? Are we clear on this part? Any question you guys might have?
No, that's good. Sorry, I'm just a little tired and I have lab soon, so I'm just kind of going along. So, but more just tired. But yeah, I'm following along.
I see. I understand. These class is hard because you have to deal with a lot of equations that might not make sense to you guys. So that's what I'm hoping to change here. I will, yeah, because once you understand what's going on here, things would get a lot more, and really easier for you guys. So okay, so let's continue. So you have that, and you derive it at, let's say, where are we at? So gonna be this one down here, right? Yeah, after I think you already know how to do the derivation, so I don't want to go through that anyway. So that's what we have, and so here it would give us the information, right? So if you want to find the voltage at point Z right here, and then we would need to, I'm sorry, at point Z, yeah. So we'd have all the, it would have plug it in, you would be able to find that voltage value. So yeah, it is used. The thing about this equation is that the value for V naught plus V naught minus I naught plus, yeah, these equation it different from different circuit, right? Like different power source, different time, different circuit, and different load. You have different value of those. So you want to define or you want to create a new parameter that is universal for all different type of transmission line that you have. So, and then you want to develop an equation that only use those parameters, right? So the idea is, I'm sorry. Yeah, that's the idea, right? So one of the equation that you, I'm sorry, one of those parameters that we want to invent it, we want to create, gonna be the propagation constant, the characteristic impedance, right here. So every time that you have an equation with all, I'm sorry, a problem transmission line, you have the power source, the length of the line, the load, you can, and then the material, the structure of the line, you can use the information to calculate these two parameters. And it will, and these two, you can apply it. These two are the universal parameter that you can apply for all kind of transmission line problem that you are dealing with. So let's say, sorry. And that's kind of going back to the idea of using math in electrical engineering. It's just like we use math to model all the thing around us, right? So all the stuff that you're doing with like calculus 3, the reason why you're doing with calculus 3 is because you want to model something in space. So in the 3D space that we are living in, you need 3 parameters for that, right? You have X, Y, Z for the rectangular coordinate system, or you can use a different system for that, which is the spherical or cylindrical. It's just a different way that we model the thing in 3D. And which one you want to use, it all depends on you. As long as you know its purpose, you use it to model them, then you don't have to memorize it. Just use the equation that you have. Same idea for what we have in right here. We have a circuit equation. So we want to model it. Then we use the Maxwell equation because Maxwell equation is the universal equation to pretty much model the thing in the universe we're living in right now with how the chart behave in the space, etc. So that's a universal model. From the universal model, we derive it is down to the formula that we can use to model a transmission line. From there, we want to simplify it more. And so we define a constant, which is the two parameter that we going to use, which is the propagation constant and characteristic impedance. So with these two, each transmission line would have a different value for these two parameters, right? You only need to calculate them, and then you apply it to the transmission line equation, which gonna make life a lot easier for us. So for that, then you would have you down to create these right here. And then, okay, let's talk about, let's see, I think I'm lost with my thought right here. And if you understand what is the characteristic impedance, like what it is and what is the propagation constant, like what they represent in general.
I'm not really sure what they represent, Charles. Propagation constant is.
Okay, so the propagation constant, I assume that after you calculate it, right, you would have it in the form of A plus JB, right?
Yeah,
A complex number. And this gonna be, it could also, I might not remember the formula, right? So correct me if I'm wrong. But essentially you can write in the way of like alpha negative J beta, right? So propagation, it means that you go in, it propagate, right? It's going to a direction, etc. So when you go into a direction, that would be two things that you want to consider, right? In this case, it's going to be the signal attenuation and the signal delay, or the phase shift, phase delay. So the alpha right here, it's going to be account for the signal attenuation. So if you go from point A to point B, the signal going to be, the signal amplitude going to go down and down and down as you go further. I'm sorry, I think I wrote it wrong right here. My bad. It's gonna be e to the alpha. Yes. Yes, it's gonna be like this. My bad. Plus or minus right here. It's not plus. My bad. Yeah. So alpha is mean that how much the signal going to be attenuated, and beta is mean just the phase shift. It's just the phase shift. So when you gonna signal come to at the end, you measure it, you will see the time delay of the signal compared to the original signal. Maybe so we say that alpha is the attenuation constant. So if alpha equal to 0, right, there will be no delay. And that's why you have it right here. It is simplified for propagation for constant. So if there's no if we expand it further, I'm sorry, I'm jumping ahead of myself right here. We know that there's reflection coefficient, right? It means that the power, how much power going to be, is going to be equal to the reflected power. And the perfect, oh man, that's not right. Okay, so it just means how much power being reflected back to the source. If there is no attenuation, if the alpha equal to 0, then the reflection coefficient gonna be the amplitude of it. The amplitude gonna be a constant. It could be a constant throughout the entire line. So if you have a transmission line right here, they reflect the absolute value of that, not the absolute value. At the reflect, if you stand on this point right here, or if you stand on this location right here, or location right here, the reflection coefficient that you see, the amplitude, it's gonna be a constant number because there's no loss here. So it means that the signal going from this point to this point has no loss right here. It only when it meet the load, then you see the reflection. But going on through the line, there could be no loss. It's just the difference in the time, which is you call the phase shift, and that's going to be the beta. I'm sorry, the beta right here. Account for essentially. So that's what the propagation constant means. So as you can see, it is that's why it is a universal parameter, because it account for it transfer, how do I say it take in the information of a different transmission line, two wire, microstrip line, etc. It take in those different information, and then it transform into a number that if we see that number, we would gain a lot of information from it. We don't have to worry about whether it is just two wire or microstrip line. We know how much attenuation it's going to receive, and what is the time delay information from it. And does it make sense to you?
Yeah.
And same case for the characteristic impedance right here. With the characteristic impedance, is pretty much gonna be the measure of characteristic impedance. So at any point on the line, right? So it's gonna be equal to the voltage over the current at any point on the line. So you have transmission line. Then if you measure the voltage and current at one point, you take the ratio, you have Z naught. So again, if you have the value for Z naught, you don't have to worry about the structure of the line anymore. You don't have to worry about what is the diameter of the two wire, what is the Y of the microstrip line. You don't have to worry about that. If it's you only know that it's going to be 50 ohm or 75 ohm regardless. So that's why these two are the parameter that we choose, because it's transform. It take a simplified thing. We don't have to deal with a lot of parameter of the line. It just give us the information that we need for our purposes. So like we said earlier, so with that being said, now the objective is still gonna be finding the voltage and the current at any point in the line that we want, right? That's pretty much solely the objective from the very beginning. We want to know what is the voltage at that certain point, what is the current at that certain point, and how with voltage and the current, we would know how much power we would want to get at the end, etc. So with that, with these parameter, we go down here and we write to those two equations that you see right here. And lossy transmission line, lossless transmission line, again, they are the same thing. It's just whether you have the attenuation constant or not. Let me see. Coefficient. Okay. Yeah. Okay. So all this point, you apply that, you will add it. So if we go back to what we have right here, let's see. So with the equation that you have right there, it pretty much tells us what it will tell us the impedance at any point of the line, right? You just need to calculate the parameter, calculate the reflection coefficient, and you're in the end you could calculate the impedance at any point of the line. Are we clear on that part?
Mm-hmm.
Okay. Could you excuse me for like 5 minutes? I'll be right back real quick with you guys.
Okay, won't be back because I will be I'm about to lab in just a little bit, so it'll just be Tabita and Hoythan still here. I'll be watching the recording.
Sure. All right, I'll be right back in like 5 minutes if you guys. All right, I'm back. It seems like everyone is gone. I see.
I think Mark left. I don't know if Ting is still here though.
Yeah. So you want me to continue? It's fine.
Yeah, just go ahead and continue. I'm still paying attention.
Just out of curiosity, has it been helpful with like to understand what this equation about and
Yeah, it's been pretty helpful. I'm just kind of like also you know, a little bit overwhelmed, but I'm sure if I go ahead and rewatch it again, it'll make even more sense. But yeah, so far it's been helpful.
I see. Because I feel like the problem that people are facing in this class is too many equation and you don't know what to use. So I hope that it could help you guys understand a bit more, so you would know what you're doing in the class. But okay. So anyway,
Yeah. And also
Wanna-
like
Mhm.
I was just gonna say also like sometimes it's just a lot of steps that you're doing and like you forget what you were supposed to do in the first place.
Yep.
Yeah.
For the impedance matching problem, I think that if you don't know what you're doing, just follow the step, then you could be really lost. So it would be important if you could see what is it that you are doing. So with a good out of what, yeah, because I think that you exam gonna be open note and open computer, open internet, open everything, right?
Yeah.
All the resources that you need, you have everything, so you don't have to memorize anything, you have them right there. So the important stuff is know what you need to do, then you could get it done quickly. Otherwise, just going through the homework, all these sample exam would not help that much.
Right.
So okay, let's go to the idea of impedance matching. So in all the time, the idea is that we want to transfer the power from one point to another point, right? So we use the load at the end to capture the power. But with the problem is the power in this case right here with the transmission line that we talking about the problem, power can be vary a lot throughout the line, and it will not be. And then the power that receive the end would not what you actually anticipated. It would depend on the load. As you know, it's going to have the equation, which is going to be the ZL minus Z naught over ZL plus Z naught, right?
Yeah.
Yeah. So in this case right here, what is it that you can control? So you want it to be zero, ideally, right? Ideally, you want it to be zero. So to have to be zero, you have to have ZL equal to Z naught. In this case right here, you have two things that you can control, right? You can either change ZL to be equal to Z naught, or you can change Z naught equal to ZL. Let's talk about Z naught first. It would not be ideal it would not be practically possible to change the value of the characteristic impedance. It is because you cannot really manufacture it, right? Like you need to manufacture them you need to mass produce them. So changing the line characteristic impedance is not going to be practical. So we only have a certain number of Z naught to work with. We would have 50 ohm and 75 ohm, right? So the other option we have now would be changing the load impedance. But again, we would not be able to control it neither, because sometimes the load that you have over there just cannot be changed, because you have an entire complex circuit that you want to power it on your transmission line. Then the load that you have right there, the equivalent load that you have with that complex circuit, is not something you could change. So this option is not ideal neither. So the other option we could do is could we somehow put an extra element here? Let's call it ZS, so that it would change the equivalent, which is right here. It would change the equivalent Z equivalent equal to Z naught. That's the idea of how maybe like you for the simple, like going back to a simple circuit problem, you have it to be 10 ohm right here at the load. And I asked you, how could you change this 10 ohm to be 5 ohm? Would you desire it to be 5 ohm? Then the answer is yes, you can put a 10 ohm right here, right? So pretty much that's the entire idea that we have in here. Maybe we just need to put an extra element here somewhere on the line with a certain value. Then the equivalent load, like we see, is going to be equal to Z naught. Are we clear on that?
Yeah.
Okay, so down here, if I were to redraw this equivalent, we would have this, right? We would have the circuit, right? And the ZS, right? I'm sorry, Z equivalent, my bad. The equivalent impedance gonna be, it will account for the ZS, the extra element that we put in, the low impedance, and then it will account for this one right here, and also the line between them. Because we cannot ignore these lines. So that's been what the idea. So if you set, so in this case right here, okay, so if we know that Z equivalent going to be equal to 50, right? Plus 0 Z. So it has no imaginary part equal to Z naught right here. So that we know. So now the problem is, can we go from this down to calculate the value of ZS? Clear that?
Was that a question? I'm sorry.
Yeah, sure.
I was just wondering if you're asking a question.
Oh no, I'm just saying, like, do you have any question on this part? Like,
No, that makes sense.
okay. By the way, if you want to leave, yeah, you can just leave. But I know you might have something else to do. Anyway. So now going back to the original problem of the impedance matching, now we know that we need to do, right? We need to need to find ZS right here. And we said earlier that Z equivalent gonna be accounted for ZS, ZL, and then the impedance on the line, which is ZL prime right there. Let's say this part gonna be ZL prime. So about these three, you can calculate these two values, right? One is given. All right, let me write. This is given. This A you can calculate. Calculator. And this is going to be equal to 50 ohm. So now you have everything that you need to find the ZS, right? The extra element ZS right here. To do that, we need to develop an equation that take in these three input and then got this input right here. So what is that equation that we have to look for? So we have the Z equivalent. If you doing that, it's going to be equal to ZS right here, and then ZL, ZS, right? And there would be two different points right here. So this could be redrawn at in the parallel combination of, let's see, ZS, and then ZL prime, I would say. Yeah, ZL prime, or Do you know what is the CL prime? Okay, I'm sorry. Let me rewrite here. So there's gonna be in parallel, and there's gonna be in parallel connection right here.
I have a quick question.
Yes.
Why did you change ZL to ZL prime?
Yeah. So right here, right, with the one that I have up here, it is not a parallel connection, right?
Yes.
It is not. But down here, I wrote it is a parallel connection, as in that ZL prime right here gonna be consist of the ZL and the line impedance right here. Let's say Z, just call it Z then, right here. So if I were to ask you what is the impedance of the line in this simple location, in this simple problem right here. If I ask you, let's say this point A and B, right? What is the ZAB here? Can you calculate ZAB for me?
Yeah.
Right? You have the formula to do it, right? I think
Yeah.
it's gonna be yeah, get a formula to do it. So, but here, wait, okay, so let me write here so you know. But let me write here so you know. Write that. Let's just say that it's gonna be A and B here. A and B. So essentially, ZAB is the equivalent impedance of the ZL, which the input impedance of the line, and then I'm sorry, Z line right here, and then the low impedance. If you take that into consideration, then at the exact point AB right here, because the line at that exact point gonna be almost equal to 0, right? So you can use the simple circuit equation for a simple circuit formula for this one, which gonna be a parallel combination. That's called as ZF prime. Oh, I'm saying ZAB right here. My bad. Did you get this part?
Yeah, that makes sense.
Yeah. So above, right? When we were talking about the line up here, the line here, when we were talking about the line here, my bad. We cannot say that it is in the parallel combination because you have to account for the line between them. So the idea is that could you maybe find an equivalent impedance at this exact point so that there would be no line between them? So you can use the parallel equation for this one to apply for it here. That's been what the idea of. That's what the idea. What we so right here we could go down and say the parallel, so we would go down and put it to be ZS gonna be in parallel with ZAB, right? And then we can find the Z equivalent, and that's where Z equivalent gonna be equal to ZS parallel with ZAB. We know we can calculate ZAB. We know the value of Z equivalent, and we can find the value of ZS. And the rest of how to do it, I think in the other problem you could see how they go into that with using the exact formula and then calculate the real part and then the imaginary part, etc. to do it. Do you have any question on this part, Tabitha?
No, that's. I think I'm good.
Okay. So with that being said, after that you could find the value of ZS, right? Let's just say the value range. Let's say you put it to be J10. Assuming let's say that you calculate to be J10, right? So you could just put a capacitor in here. I'm sorry, not capacitor, the inductor in here. Calculate the inductance values of the inductor. Put it in between at the location that you calculate also. You got pretty much the job done. Yeah, but in practice, it is pretty impractical to just put an capacitor or inductor, right into the line. It is not practical to do that. So what we do is what we find out is that in the case with the transmission line problem, in the case of short circuit or in the case of open circuit, what we find out is that the impedance right here is behave like in capacitor or inductor. So in sorry,
Uh,
can
I
you hear me
think
now?
you're muted. I think you were muted for a bit.
Yeah, sorry, my bad. Yeah, so we find that it can just going to behave like a inductor or the capacitor. So you from here you go up here and you can have the equivalent circuit to be like this. ZL in the position that you put VS, you would just need to pair up wire. Whether that pair of wire is short or open is your choice. Are you clear on this part, Tabitha?
Yeah.
Do you have any other question? Because that's pretty much a lot. I have to end the session soon.
Yeah. I think that I'm good for now. Yeah.
Yeah, it's probably I probably talk a lot between of them, but yeah,
No, you're fine. Y'all are still having office hours or no?
probably not. But if you have any question, just send me an email or a message on Team. I'll answer you quickly.
Okay.
Okay.
Thank you.
See you later. Bye bye. How's it going, Nick?